happy to have you here for another session of the Lisbon AI Seminar. Today we're going to have Francisco Laranjinha. He's actually here, PhD candidate at the Center for Philosophy of Science at the University of Lisbon. And he's going to talk to us today about the crisis of scientific production in the age of AI. Please go ahead.
Well, so the first thing that I want to note is that computational physics has had a huge success in scientific production. So we can widely employ and use models and computational simulations in physics, in astrophysics, in particle physics, in condensed matter physics, in fluid dynamics, in quantum mechanics, in cosmology, in nuclear physics, and biophysics. And this is why it's successful. But why do we use it? So why do we use computer simulations in order to study a system or a natural system? And why are physicists, getting a grasp of such tools? Well, first of all, when we're studying a natural phenomenon or a natural system of any sort, they turn to be very complex to study. So to study a physical phenomenon or physical system, usually what we need is to find a set of partial differential equations, and we want to solve them. To solve the partial differential equations of a system usually means that we're solving the system, we're getting a solution for the system. And usually it's very difficult to solve those equations. In many instances, there's not even an analytical solution. So we use computational simulations. So we can also use it, and this is very important in the case scenario of AI. We can use computational simulations as a laboratory. So we can, when some sort of systems are very hard to figure out what you're doing or to experiment them, we get data. So we can simulate huge amounts of data, and we can use computers to be our laboratory. So in quantum mechanics, for example, when we have a given phenomenon that is very difficult to study or very difficult to experiment, we simulate it in a computer. And it's an intellectual level. So again, in many case scenarios, it's very difficult to grasp visually or to understand what the system is doing. And by using computational simulations, we can visualize and conceptually understand way better and in a very simple manner the system that we're studying. So for example, quantum resonance tunneling. What is quantum tunneling? So we're throwing the electrons to a potential of energy, and it goes through. So we can visually use a simulation to figure out what the system is doing. Okay, so it's a bunch of techniques that are employed in computers that help scientists to figure out way more and to think way better about a given system in study. What does this have to do with AI? Well, AI is just, first of all, we need to figure out, to answer these questions, we need to figure out what is AI? How should we view the use of AI in scientific practice? What should we reasonably expect it to do? And if this is any sort of revolutionary in any case scenario, in any sense. So what is AI? The general definition given by Code in 1970 is that it's the study of how to build or program machines to enable them to do all sorts of things that minds can do. So this is the general definition. Well, it's very problematic. So what is exactly things that minds can do? So how do we program those machines? So it's not very easy to grasp this idea at first. And second of all, in many cases, people view AI as the study of intelligence as such. So again, problematic. So that would be the strong definition. But having a weak definition, we can erase many of these problems. So you can say AI is the development of machines whose observable performances has features in which humans we would attribute to mental processes. So to solve a given partial differential equation. That is very, very important because when we're using a computational model to solve a partial differential equation, the model is not really solving the equation. It's a tool. The difference from AI is that it has a degree of autonomy. AI can solve those equations by themselves. So the computational model that we use in AI can solve those sorts of equations. So how should you view this in scientific practice? Well, the starting point in this is actually this is just one references, but we select two. So Turing in 1936 and Turing in 1950. I think this one is very important because he states the question: can a machine think? So and for Turing, this question was very recent. So of course, a machine for Turing in Turing's view wouldn't do the same sort of thinking that a human. The question for Turing was a question of imitation. So can a machine imitate the human behavior well enough so it would be undistinguishable from a point of view, an outsider point of view C? That is the question that Turing proposed. And if a machine can imitate a human in such a way that it would be undistinguishable, my view is, or my research question is, can it produce new scientific knowledge autonomously? So if you can imitate a human, and if you can imitate some and some aspects that humans do, some behaviors, it might be able to imitate scientific production or some sort of scientific methodologies. Does this question make any sense? I mean, well, let's propose a variation of the Turing imitation game. It's a scientific imitation. So, in order to figure out if, an AI model can produce new scientific knowledge, we will first, define the criterion to produce scientific. And let's define it very broadly as whatever the scientific community accepts as knowledge. So the scientific imitation game is a variation of Turing game, and we'll just propose the following. There's a reviewer, scientific reviewer C. I'm a scientist, I am, and I make a paper. So I can use whatever tools I want. I can use computational models, not AI models. Anything I want. I can use a pen and a paper. I can use calculators. I can use a computer, whatever. And I make use of a certain methodology. For example, I go to the laboratory, I gather data. With that data, I find a mathematical model that fits that data, and I describe the mathematics equations that give me the relationship between the data, the quantity relationships, and I state, for example, oh, force is proportional to acceleration through a constant that is the mass of the object. So this would be a scientific research paper. The question is, can I have a model, a computational model, an AI model that does this on their own, that is indistinguishable from my own scientific paper? There will be an interviewer C or a reviewer C looking at both these papers, and if you cannot find any difference, we would, successfully have produced new scientific knowledge autonomously. An AI would do it. Could it do it? Is it possible? Well, yes. It's already made. The Turing game was already beaten by machines, and this specific formulation was already, done. An AI can indeed produce some methodologies or some scientific methodologies on their own. Is it any good? And why is it reasonable? I mean, why? Why should AI be able to produce such a thing? And what should we reasonably expect it to do going forward? Well, to demystify the notion of AI, we have a very broad definition, but there are a bunch of there's a bunch of tools and ways to do AI. Robotics is a form of AI. So, for example, if I can build a robot that ties my shoes, well, this fits the weak definition that I gave earlier. So, robotics is a form of AI. I'm focusing on deep learning. So, machine learning is a subset of AI. And inside machine learning, there's deep learning, which is a subset of machine learning. So machine learning is the science that tries to build in models, computational models in a computer that we refer to them as neural networks. And how do they work? I have an input. So x1, x2, and x3. So these are the first neurons. That's the first layer. What a neural network does is that it gathers an input and gives me an output. A neural network is nothing less besides a function. It's a mathematical function. It takes three numbers. This one specific takes three numbers. And what does it do? It sets features. It sets parameters W, which is weights. It multiplies them by the input, and it adds or subtracts another parameter which is the biases. What does this do? So I can connect each input to a new layer and new neurons. Neurons are those circles that are nothing but functions that hold numbers. So I can connect numbers to this different layer, and I can do the same process, connect it to another layer, and I can just connect it to the dimension of the output that I want from my neural network. I can have a whole bunch of architectures. I can have more input, more output, less input. I can have more layers, different architectures. I can have situation neural networks. But what this is, fundamentally, is a matrix. So it's a system of equations. I have equation 1, equation 2, equation 3, and I multiply 3 by 4. I have 12 equations. And then I multiply 4 by 6, another 24 equations, and it's a matrix. So a neural network, a model of AI, a traditional model of AI, is a mathematical structure. How does it learn? And what does it mean to solve a problem? This particular neural network has 52 parameters. So 3 times 4 times 6 times 1 plus the biases. Each parameter are the weights and biases. And how does it learn, really? Something called gradient descent. To fit a model, we need a training set. So data, input and output. We seek parameters, which is our weights and biases, that we use in the model to have an accurate mapping from the inputs to the outputs. So we define a loss function that is just any function that I want. I mean, of course, it has to be useful for the system that I'm studying. And we are quantifying the difference between the outputs given by my neural network and the outputs that I want my neural network to give. This mathematically just means to find parameters, weights and biases, which minimize my loss function. How do I train my neural network? I give, random parameters and biases. I get an output, and I look at my output, and I look at my, expected output, and I say, oh, this is rubbish. You're not working very well. I adjust my parameters, and I try to using my loss function, and that loss function is just, for example, the difference between the difference of the squares of my output and the training set of data of the output that I wanted to get. How do I do it? So I have different outputs, and first of all, if I want to minimize, the function that minimizes the parameters of my neural network is the gradient. So I derive my loss function throughout each of the parameters that I have. With that derivation, I just see, well, what is the minimum of this function? That is exactly what this does. Calculus 2, it's a calculus exercise. I minimize it. I see the difference. You say, so is the difference getting lower? And if it does, well, I just continue to go through my differences until I found a local minimum of my function. And I've successfully trained my neural network. So it's not magic. So it's actually a calculus exercise. To learn or to solve a problem for an AI model just means to solve a given calculus exercise. So to say that they reason, not think really, because this is a problematic word thinking. But to say that neural networks reason because they recognize patterns, well, this actually means that they solve a given calculus exercise. For example, in our neural network, handwritten recognition. If I want to recognize a handwritten number, I give an image, 28 by 28 pixels, for example, and I just see, okay, so my input dimension is 28 times 28, 786 parameters, and each neuron, each one of those 786 parameters have a number. I associate it, for example, to the first layer with 16 neurons, second layer with 16 neurons, and an output from 0 to 10. And my training network just, picks those 786 neurons and tries to figure out what is the output that best makes my input. 13 and 2 parameters, that's the number of neural networks that I just described. Not magic, just calculus exercise. And when we see this this reasoning and learning in AI, we can have a grasp of what it does. My point is that to answer the question, what we expect it to do in the future, we must answer the question, what is it doing now? So what is it doing? We can clearly see that despite solving an analytical calculus exercise, this is very different from traditional computational models. And it will solve a whole bunch of problems that traditional computational models and simulations will not solve. So, for example, why? It has an autonomy character. So it does those types of calculus exercises on their own. AI, generative AI, what is it? So, for example, when we are generating an image, we generate that image through a bunch of statistical procedures. So we are generating numbers. When we are generating a specific number based on the input and the output that I have, based on a training set that I'm using on that neural network. So, for example, let's give just quick example so you can understand. When I have an image of a cat, I train my neural network with images. I have a bunch of patterns on a cat, and I have statistical correlations from those numbers to the output. I generate a neural network with a given mathematical model that generates similar patterns, and I will generate images of cats. It's very complex. It's a very complex calculus exercise. Some of them, our most sophisticated neural networks have, thousands of parameters. They're really, really huge, but they're just doing calculus exercises, nothing more. And is this revolutionary? So why should this be revolutionary? I mean, this is just a tool. So it's a tool that scientists are using with a degree of autonomy, but why revolutionary? Well, let's consider physics, and I'm just considering physics here. I don't know if you all know Noether's theorem, but Noether's theorem states that for every continuous symmetry in a physical system, there's a conservation law. So a symmetry of a physical system means just, in the context of this theorem, a transformation to the system that leaves the equations of motion unchanged. What do I mean? I have two particles, let's say the sun and earth. And let's imagine that they're all at the same distance from each other. Let's imagine that the path that takes from the sun is a perfect circumference, and the distance from the sun and earth is always the same. If I pick the sun and earth and translate them to another place, so if I add a vector that is the same vector to the sun and to the earth, my initial arranging system will not differ from the final arranging system after this continuous symmetry. Why? Because the kinetical energy does not depend on the distance of each particles, and the potential energy, if it's just the gravitational potential energy, just depends on the distance that each particle has from you. And that distance didn't change. That's by symmetry. This implies, on Noether's theorem, that I find one of the most fundamental conservation laws in physics. The linear moment is conserved through a symmetry. The question is, could a neural network do it? Well, yes. From what I've told you, mathematically speaking, it should have no problems in finding a symmetry. This a neural network could do very, very, very well. But is physics all about symmetries? You know, and with that question, I'd like to focus on particle physics. So why particle physics? Because in particle physics, that just means that when we describe mathematical particle physics, we're just trying to describe a given symmetry that corresponds to a particle. So, for example, you want symmetry of quantum electrodynamics. SU3 group symmetries in quantum chromodynamics, flavor symmetries, discrete symmetries, parity, charge conjugation, time reversal, discrete symmetry transformations, space symmetries. To find symmetries, a neural network should find very well, provided what? Good training data and the right architecture. No problem. Why? Well, space-time symmetries, for example, they're just described by the Lorentz transformations. So why should we be able to find space-time symmetries? Well, because we have 6 degrees of freedom. This is the sign of all physicists. All physicists, say hello with this. Why? Rotation on the x-axis, rotation on the y-axis, rotation on the z-axis, boost on an x in the x-axis, boost on the y-axis, boost on the z-axis. 6 symmetries. With these 6 symmetries, I find special relativity. Time reversal. So for example, when I say to do a process, a ball falling or an object falling now, and 10 minutes later, just means that energy is conserved, because it's the same process. The ball does not care if it falls now or then. It just cares about the height from its fall, and where is it falling. If it's on planet Earth, acceleration of gravity is 9.8. If it's on Mars, is 3 times less. That's it. This symmetry on time implies conservation of energy. For example, charge conjugation. The symmetries on charges implies charge conservation. So, for example, when a particle is decaying, if it's decaying, charge must be conserved. Simple. So, how could we find all those symmetries using neural networks? Well, we gather the data, we train our neural network to find that symmetry with the right architecture, and now we have foundational models. We have models that find the symmetry that I want to find. Okay? And there's a new thing, I don't know if you recall, about generative AI, to generate new data. So a computer can be a laboratory. And can I use? Yeah. Okay. So imagine this. Imagine that you have square, then you have a circle. You know that the area of the circle is 5 r squared. How do I find the area of this circle using computational simulation? Simple. I have this L, I have this L, and I generate random data on this curve. And then I sum the numbers inside the circle. That sum will give me the area. I've generated data using computers, and I can do that using AI. What is the epistemological problem? When I'm studying a given theory in physics, or I'm studying a given, a given system that is way too complex that I cannot test in a laboratory because I do not have the technology to do it, I will just generate the data that I need. By generating the data that I need, I have my training data. My question is, how do I know that that data is actually truthful data? Truthful empirical data about the system that I am studying. I have all these symmetries. All those symmetries are important, but I also have mathematical symmetries that relate have absolutely nothing to do with any physical thing whatsoever. A symmetry is a mathematical structure. I can find symmetries, but why this one, not any other given symmetry on the physical system that I'm studying? What should I tell my neural network? What is the symmetry that it's supposed to find? Well, as you can see, this tool is used absolutely successfully. It will solve problems that are beyond our imagination. The same way that computational models, computational models, as you might have seen on our first slide, when I was studying quantum mechanics and they told me about quantum resonant tunneling. What do you mean you're just throwing an electron? Are you throwing a little ball? But it's a wave. How does it go through a potential, barrier, an infinite potential barrier? Well, like this, we can visualize way better our system. But imagine that we hadn't tested. We didn't have the technology to test that experiment. Does this tell me that electrons actually go through a potential of energy if I didn't have the experimentational set to do it? Well, this is the same question with AI. So, for example, what symmetries should I find? Out of all this, what are the symmetries that I should look for? And is solving scientific problems in physics just a matter of building a good computational model? So all what we want to do when we use artificial intelligence in scientific practice, all we want to do is build a computational model using AI that solves the problem that I want to solve. Is this science? Well, is this science because this is accepted by the community, by the scientific community? Well, then why? And this is not just a singular case. There are many cases of this. Why then scientists use ChatGPT to generate an entire paper from scratch, but they just don't want it. You know, why did scientists have to retract that paper? The scientific community accepted it at first, but then it realized it was made by an artificial intelligence, and now it's not good. Why? Do we need to find new conditions for what we consider to be science? Or better said, for what we consider to be good science? For example, in the case of the definition of artificial intelligence and to mimic intelligent behavior or intelligent better said, I don't think that nobody would disagree that to do science one needs intelligence. You know, to figure out Planck's concept, for example. In 1900, Planck gives a postulate about energy. So it states that energy is discrete. Now, why did he make that hypothesis? Why did he make that sort of thinking? An AI, given what a neural network is and what it is now, will never be able to do it. It has no semantics. It's a mathematical structure. It's a matrix. It's a system of equations. It will never be as it is now. I don't know if it will ever do it, but considering our AI right now, it will not generate hypotheses. Isn't science supposed to generate hypotheses about a given system of study? Or are we satisfied with building computational models? And second of all, does better problem solving skills imply better science? So for example, I think let's start from the principle that we all agree that in the beginning of the 20th century, we've had a scientific revolution in physics. We had a new language, we had new theories, we had new problems, we had new mathematical foundations, we had new everything. We had a new paradigm of science completely. We formulated general relativity in quantum mechanics, right? So this didn't actually provide us with problem-solving skills. It provided us with a different view of nature, a completely different view of nature. Can we just state that by having artificial intelligence solving problems that we took us, I don't know, now take us, can we say that by better science? And, the more general question that I've been, scratching, what does it really mean to produce science? If the scientific production means anything that the scientific community accepts as science, then, nature has no reason to retrieve articles just because they're made by AI. Very sorry. But why? If they've done it, not just Nature, but other scientific magazines, if they retract the articles because when they know that scientists that AI is making them, we have to find new conditions. And should be argued in favor of experimentation. So with generative AI, I can generate new data, I can generate large amounts of data. But should we state, and go back to what Poincaré said, should we just view, that if you don't test it, if you don't experiment, if you cannot build technology with it, you have no reason saying that actually says something about natural systems. not saying that, we shouldn't build those types of models, we shouldn't be doing fundamental theoretical physics, that's not it, but we should really try to, or should we try to find epistemological claims about natural systems using experimentation, or are we satisfied with using computers as a laboratory? Way more sophisticated now with AI than they used to be with computational simulations. Well, those are my questions. Thank you. If you want, I have references. If you want to ask anything about a given specific topic, I can give you references. And any further questions, ideas, lines of thought, share, and thank you. You're welcome.